Professor Jan-Willem from the Meent. So Jan-Willem and I just discussed about his trajectory, which started in physics, and he spent quite a bit of time here around Cambridge, and then went back to the Netherlands, where he's now leading the Amsterdam Machine Learning Lab, and is also directing the ELIS unit in Amsterdam. And the floor is yours.
Good. All right. Thank you for this invitation, and also kind of for the nice talks today by the other speakers. So I am going to give a tutorial today. So this is a talk that's designed to be somewhat pedagogical. And what we're going to talk about is flow matching, and specifically kind of a variational perspective on flow matching that we've developed. And what we're seeing is that there's lots of applications in the physical sciences for these types of technologies. This is work that where kind of the common denominator is my PhD student, Floor Eichelboom, and he's accumulated this whole kind of gaggle of collaborators over the last couple of years. Like, the names no longer fit on the slide, and so I'll be pointing out kind of some of the work kind of we've been doing with these people over the last couple of years. So before we start on kind of flow matching kind of proper, right, I like this kind of start my talks reflecting on where we are kind of in AI today. And I think, you know, this is a workshop about, I guess, AI across skills, right? But AI itself is now also kind of operating at kind of a phenomenal scale. And you could say that we've basically reached the thermodynamic limit of compute. Because if you look at kind of the training costs to train kind of serious LLM, you arrive at a number which is something like 10 to the 25 floating point operations. So you could measure this in moles, right? You could say, let's start measuring kind of the training cost of our LLMs in Avogadro flops. And so then, you know, you end up with a number like 17. And you could kind of play fun games. So like, I started my career in fluid mechanics. You could say, well, if kind of flops were molecules of water, what volume of water do you get if you have 10 to the 25 kind of molecules? Anyone in this room willing to do a rough guess? We all did this in high school, right? Like, you probably had to do this as an exam question at some point in your life. No bad answers, right? So it is kind of a macroscopic number. It's about a glass of water, like kind of something like 300 kind of milliliters. And back when I asked Claude to do this kind of exam, it then told me that this is slightly more than a typical can of soda, which Claude thought was 250 milliliters. This is a strange number. I looked this up. There's no country where a typical can of soda is 250 milliliters, as far as I can tell. And I think this is a perfect kind of illustration of where we are, right? Like, these models are getting better and better. I don't know who's using things like Claude Code now, like particularly these coding kind of models have gotten so good in like the last couple of months. And then every once in a while it gets something wrong where you're like, how did you do that? But so yeah, it's like, there's an analogy by Alex Alamy, who I was talking to at some point back, and he said, yeah, it's like we're pouring kind of compute onto this problem, right? Like, we've really kind of hit the thermodynamic limit. And of course, this means that we're in this kind of strange narrative, right? Like, it's very clear that AI is going to enable development of new technologies. And of course, we like to talk about how this could also potentially help us with the energy transition and develop clean technologies. And at the same time, we see that companies are investing in nuclear energy, co-locating their data centers kind of as close to kind of power sources as possible. And, you know, every once in a while, when somebody wants some attention, they'll say something about putting data centers in space, or maybe a Dyson sphere, right? And I think, yeah, I guess what I'd like to say is I take both these narratives seriously, right? Like, I do think that there's a lot of computational problems in AI, in the physical sciences, where in some sense what we can do has been limited by kind of the numerical methods we have, and those have been, it's not like there's no innovation, but like a lot of those have been around since the 90s. And I do think there's opportunities where AI can really help us do computations that we weren't able to do before, and I think that will lead to inventions. But at the same time, I think we have to start taking kind of the energy usage associated with AI more and more seriously. Okay, so let me situate kind of the tutorial today in terms of kind of scientific computations more broadly. So I think we're kind of very interested right now in classes of problems where what you're trying to reason about are kind of possible structures of molecules or maybe possible structures of materials. Or you could also have something like a program synthesis or a model synthesis problem where you're trying to reason about kind of the graphical structure kind of that underlies your data. And so these are all kind of discrete structures where kind of there's a combinatorial explosion of possible, points in your hypothesis space, so to speak. And I think in this setting, kind of generative AI can help us in a particular way, right? We can pre-train a model that basically gives us a type of prior over these possible structures. And we can then say, well, if we want a molecule that has particular kind of characteristics or a material that has particular characteristics, then we can frame kind of identifying kind of the subset in this hypothesis space as kind of a guidance problem in the diffusion model or flow matching model. And today kind of we're going to talk about this kind of variational perspective on flow matching. And what you'll see there is that this kind of perspective on kind of using inference at test time becomes particularly natural. So the structure of this talk is basically we're going to talk about flow matching. I'm going to tell you a bit about kind of how this connects to test time inference. And then I'll close off with some recent work we've been doing on few step generation. So I should probably know kind of diffusion models and even flow matching need upwards of kind of 10 steps during generation. We're now getting to a point where we can sometimes get good results with 2 steps or sometimes even 1 step. And I'll tell you a bit about kind of the innovations on that side. Okay, so let's start kind of the actual tutorial part. So I like to kind of describe flow matching as really a simplified perspective on diffusion. Right, like in diffusion, in flow matching, you interpolate between kind of like a starting distribution and a final distribution, and typically the starting distribution is just Gaussian noise. And the most common interpolation in flow matching is a linear interpolation. So we're just saying we're going to define a noisy sample, let's call it Z, and that's going to be like time times data, 1 minus time times noise, and time runs from 0 to 1. So at time 1 you're at data, at time 0 you're at noise. And once you have this interpolation, this defines probability distributions. There's a distribution over noisy data points given kind of clean data points. And there's also a posterior, which is the distribution over clean data points given your noisy data point. And what you now do in flow matching is you try to approximate an ordinary differential equation. So you say, I'm going to start at noise, I'm going to integrate this differential equation over here. And what does this differential equation say? What we're going to do is we're going to compute a velocity. And this velocity, if you look at it, it basically says, look at where you are, look at where the data is, and move in the direction of the data. And at any point in time, you're going to have 1 minus t time left. So you're going to move towards your data at a speed where you're going to reach the data point exactly at time 1. Yeah? And so what this tells you is where to move if you know what data point you're going to eventually arrive at. But of course you don't actually know what data point you're going to arrive at. There's a distribution that's this posterior, right? Like there's some distribution over possible data points that could have given you this particular noisy sample. And so in order to kind of compute this ODE, we're going to have to compute an expectation with respect to this posterior. But since this thing here is the only thing that actually depends on our data, really what we need is the mean of this posterior. If we can approximate the mean of this posterior, then we can solve the flow matching problem. And maybe for those of you in the room who have thought less about flow matching and more about something like score matching, there the problem is entirely analogous. Like in score matching, you have this score function, and you can define this kind of in terms of kind of the score function you get if you know what data point you're going to end up in, and then you also have to take an expectation with respect to possible data points. And so very often you can translate a flow matching problem to a score matching problem and vice versa. like a bit more precisely put, there's a probability flow formulation of diffusion, and that basically is the same thing as flow matching under certain assumptions. Okay, so let's do kind of an example here to get some intuition of how this interpolation works and how kind of integration works. So here I've written things a little bit differently. I've said I'm going to call mu the mean of this posterior. So this is the expected value of data given your kind of noisy interpolation. And now I can describe this velocity as kind of my expected data point minus where I am divided by the time I have left. Okay, so let's kind of plot something so that we kind of have an example to look at. So suppose that we start here. We at the left side here we have just a kind of normal Gaussian distribution. So that's something that's easy to sample from, and eventually we would like to sample from something that may be a bit more difficult to sample from. This is a bimodal Gaussian. This is still easy to sample from, of course. So one thing to realize is that when we're going to be training these models on data, we actually don't have the data distribution. What we have is some sort of kind of finite sample empirical approximation of our data distribution. So really kind of the picture we should look at is a bit more like this. Okay, so what happens now, right? Like at each point in time, we need to compute this quantity over here. So we're going to pick kind of a point at random from our kind of noise distribution, and then for that point, we have to calculate the mean of the posterior. And so here I've plotted kind of the posterior at time 0. And the thing you'll notice is that the posterior here looks exactly the same as the data distribution. And this is reasonable because at time 0, you're multiplying data by 0, and so all you have left is noise. So there's actually no correlation between kind of where you start and the data at time 0. That correlation gradually comes in. So what are we now going to do? We're going to compute the mean of this distribution, and we're going to move in the direction of this mean. And we're going to keep doing this. And now if you keep kind of your eye on this distribution on the right as we're kind of integrating, you see that this distribution begins to shift. Right? It starts at a distribution which is just the data distribution, but as you're kind of progressing during your integration, there's kind of a smaller and smaller subset of data points that could have given you this particular noisy interpolation. So this posterior becomes more and more sharply peaked. And eventually, kind of as you approach, you converge on basically a delta peak on a single data point. Right, so this is kind of the ODE that is being defined by kind of this flow matching problem. And the computational problem is now to approximate this ODE. Right? Now, traditionally in flow matching, what you would do is you would say, I'm going to define some form of neural network that computes basically everything here. So, so I'm going to compute everything here, and I'm going to just learn this velocity field. And the way you could do this is you could just define a loss. You're going to take your velocity, but also you're going to sample an x and an epsilon, and for the linear kind of interpolation between those two, kind of, there's just a constant velocity, which is the difference between these 2 points. And then you just do a squared loss kind of regression. And this is fine. Now, what we're going to talk about today is this kind of variational perspective on flow matching. And this is really something that's very, very simple. What we're going to say is, well, if I know I can express this velocity in terms of a posterior mean, why not just learn this posterior mean? And so what I can do is I can define some form of variational distribution over data points given my noise, and then that variational distribution will have some mean. And this is actually a really easy loss, right? This loss is just a self-supervised loss. And what's nice about these problems, like flow matching and diffusion, are the same in this regard, right? Like all of these problems, you can really think of them as self-supervised learning problems. You start with data, you make noisy version of your data, you always have the label, which is the original clean data. And so here, what you're literally going to do is you're going to put both of those in your variational distribution and do maximum likelihood, right? And what's now nice about this? Well, One thing that's nice if you like kind of probabilistic formulations of machine learning is that it's a nice probabilistic formulation of machine learning, and this may give you kind of a warm, fuzzy feeling depending on how you were raised, right? Like I was raised as a good Bayesian, so like I somehow still feel, I feel sympathetic to this. But what I think is also useful is that now, right, you've explicitly framed this flow matching problem as what you could call self-supervised endpoint inference. Right? You're just explicitly predicting where you think you're going to end up. And as we'll see, that gives you kind of a better link to kind of Bayesian inference methods, also things that you can apply at the test time. But maybe the more important thing is you can now deal with all sorts of data modalities. And this is relevant to the sciences. So you might have categorical data, you might have Poisson data, you might have, I don't know, data from a gamma distribution. All of those things, it now becomes trivial to say, I'm going to write down a variational distribution where kind of the support of the distribution matches the support of the data distribution. And it turns out that that actually works a bit better than just treating the problem as if you're sampling from a Gaussian, even when you're not. And so we'll look at some examples of where we see that this actually does work a bit better. So we started originally applying this to graph generation. So think kind of these kind of data sets like QM9 and Zinc. And because that's categorical data, we call this model CatFlow, and you'll see some bad puns coming in the papers afterwards. And really this worked great. Like if you look at, I think by now, right, like these benchmarks like QM9 and Zinc 250 are maybe not kind of the most serious benchmarks, but if you compare it to kind of other methods, including kind of methods where you do discrete diffusion, so like you kind of sample a discrete state at each step, we broadly get kind of state-of-the-art results in that setting. Something that is maybe not obvious is that this also helps when you're generating images. So kind of a lot of the kind of state-of-the-art image generators, they actually use some form of like VQ-VIE type kind of pre-trained model. So what you're actually generating when you're kind of generating using diffusion or flow matching is a set of codebook vectors, and all of those codebook vectors come from some vocabulary, and then you have a grid of these codebook vectors. You run that through a decoder at the final step to get your final image. So if you're generating data that is discrete, basically tokens in a latent space, then it turns out that if you treat your data as discrete, you get slightly better results. So, we tested this, and so this paper is called Perception, and so like you may now start groaning. And this got accepted at iClear actually. And so, we tested it. Here's kind of like some sample images. This is maybe the most informative plot in the middle. So we're comparing to regular flow matching and variational flow matching where we're treating our data as Gaussian. And then the blue line is kind of the actual perception model. So that actually works a bit better, and it actually works a lot better than the kind of discrete flow matching baseline. So these are the kind of things where you treat every step in the trajectory as discrete. And I guess the contrast here is that flow matching kind of encodes into the problem that your data at time 1 is going to be discrete, but every step along your interpolation is still continuous. It's worth noting that people have actually already done this for language models. Way back in the day, there was a paper called Continuous Diffusion for Categorical Data. That's by Sander Dieleman and a whole bunch of people at DeepMind. I suspect that that paper actually forms the basis for Gemini diffusion, which you may have heard about. And so that's also one of these models where you treat the kind of data as kind of discrete, but the kind of trajectory you're integrating is continuous. And at some point after we wrote CatFlow, we went back and we realized you can map these kind of equations onto each other one-to-one. They derive everything through the language of kind of score matching. We derive everything through the language of flow matching, but like there's an equivalence between those two. Okay, so we also kind of did some kind of additional work in kind of a setting where what you may want to generate is angles, positions, and maybe atom types. So now you have two types of continuous variables, angles, which you can model as Gaussians, but Gaussians on kind of a sphere, so like you could use like a Riemannian Gaussian posterior. The positions are just Euclidean, and then the atom types are categorical. So, right, like in the past, it was not quite clear how, if you have the diffusion model and you need to kind of generate these different types of variables jointly, how you're going to do that. From the perspective of flow matching, this becomes basically trivial. Well, I shouldn't say that our students' work is trivial. It becomes conceptually straightforward. You then still have to do it, right? Like there's a difference between those two. And so we did this. We applied this to kind of some metal organic frameworks, benchmarks, and there kind of once again we're getting kind of competitive results. There's also kind of people who started using this stuff basically within a year of our original variational flow matching work coming out, and a lot of these applications are kind of sciencey applications. So here's an example where kind of offers, we're not part of this, right? This is a different group of people, are applying this kind of variational flow matching to sea ice simulation. And kind of the main idea is once again the same, that like if you're modeling sea ice thickness, you want some sort of kind of positive definite kind of variable, and so it just becomes easier to parameterize it this way if you use this kind of the variational perspective. And something similar here, this is a recent paper on kind of transcriptomics, and here kind of the parameterization that turns out to be helpful is to use a Laplace posterior for kind of the coordinates of cells, and then use a Gaussian posterior for the gene expression within the cells. Okay, so I've now told you about, I guess, basic flow matching and kind of this variational perspective on flow matching. I'd like to spend a bit of time talking about why this is also a useful perspective in the context of test time inference. So let's first briefly establish kind of what we mean by that. So, right, we had this example earlier where we were trying to generate from a data distribution. So now imagine that this is two peaks, and so we could assign labels to these points, right? We could basically say there's this peak 1 and there's peak 2 because this is a mixture model, and you could now ask, suppose I want to generate only from one of the peaks and not from both. Could I condition my model in such a way that I guarantee that I'm going to generate from one of the two peaks? And because this is a simple example, you can compute this. So right here's kind of the distribution over possible interpolations if you condition on the fact that you're going to end up in the bottom peak. And from kind of, in many ways, right, nothing much changes here. Like previously you were approximating the mean of a posterior. And what you now have to do if you do conditional generation is you have to approximate the mean of a posterior that's also conditioned on this additional value that you specified, this value y. And one thing that you can do trivially, just like in diffusion, is you could just say, okay, I'm going to have some network that predicts this mean. And instead of giving this network only kind of my noisy sample, oh, I should have put z here, sorry, that's a typo. I can also give it kind of my value y. And then what you end up with is kind of the equivalence of what you would call classifier-free guidance in a diffusion model. What you can also do is solve this problem at test time. And so that means that you just right, you assume you don't have access to any labels during training, you just pre-train a model. And, you know, particularly if this is a big model, right, like a language model or something like that, or an image model, this is a useful thing to do. And then at test time, you either specify some sort of label and a classifier, or more generally, kind of like some notion of reward, and then you could treat kind of generating according to this classifier or reward as an inference problem. And so let's do an example to kind of see how that works. So, right, like here's our previous example where we have the distribution over data points given noisy interpolations. So what I can now do is I can treat that as a prior. And I can now define a likelihood, which is kind of the probability of your label given your final data point, right? So this is given clean data. So for people who are familiar with diffusion, right, you have classifier-based guidance. You usually train that classifier on noisy samples. Here we're saying you somehow have a classifier based on clean samples, which I think is a much more kind of, like, that's not a high bar to clear, right? Like that, quite often you have that, or you can train that. And so now if you multiply these things together and you normalize it, you get your posterior. And so in this particular example, here's what the posterior looks like, and it's exactly what you would expect, right? It basically just zeroes out all the points that are in the wrong peak, and so you're just left with a hypothesis space of all the points that are in the correct peak, and then you can do your generation as normal. And so this kind of like test time inference is becoming, I think, more and more important in the generative AI space. We're going to talk in a second about kind of like all the kind of Bayesian inference methodology that you can now kind of start kind of in some sense dusting off, right? Because we thought that we weren't going to do this anymore because we're all doing deep learning. And you know, particularly for problems where, I don't know, you're generating some material or some molecule, right? Like you can't really make a training data set with all kind of objectives you might have at test time. And so, you know, even if you do kind of some adaptation at training time for guidance, you know, it's still useful to be able to kind of clean up your samples with this type of test time inference. And so, you know, we also wrote a paper about this. This was ICML 2025, where we kind of just tested some basics here for kind of molecular generation. And we tested a couple of schemes for kind of solving this Bayesian inference problem, a Laplace approximation and something kind of iterative. The thing that I would like to point to is that kind of these days what we're seeing more and more is that actually people are using these models as part of a sequential Monte Carlo procedure. So you could take your pre-trained model, that's kind of like a prior, you could actually make a guided model that becomes a bit like a proposal, and then you can compute kind of corrections and kind of do something called resampling. And then, you know, you're spending quite a bit more computation at this time because you may have to generate, I don't know, up to 100 samples, but that does mean that, you know, you can solve your guidance problem. Here we're doing just kind of much more simple things, and what we're seeing is that kind of on these benchmarks like QM9 and GM drugs, we're getting kind of good results. Okay, so I'm going to take the rest of the talk and kind of talk a bit about what I think is an interesting kind of emerging direction of research, which is kind of these models for kind of few-step generation, and we'll connect this to these flow matching approaches as well. So one way that people talk about few-step generations is in terms of a mathematical object that you call a flow map. And the relationship between kind of flow matching and flow maps is very simple. In flow matching, what you say is, well, you know, I need to integrate an ordinary differential equation. So the thing I have to approximate is basically the time derivative in this ordinary differential equation. And then at test time, I need to either do Euler integration, or if I want to get fancy with it, I could do Runge-Kutta or some other integrator, right? In flow maps, you say, well, okay, I could just also just directly predict where I think I'm going to be at time t if I know that I'm starting at a particular position at time s. So this function, the flow map, is just the solution of the ODE, right? And so rather than approximating the ODE, you could directly approximate the solution of the ODE. And one thing that people often do is rewrite this slightly. So they say, well, this is wherever you started, and then this is basically your time interval. And then you could, by definition, call whatever the displacement is, the displacement divided by the time interval, you can then call the velocity. And people refer to that as a mean velocity, right? And so the point is, we don't know how to compute this, we don't know how to compute this either, right? So we're going to have to find a way of approximating this. Now, the observation we can immediately make in the context of these types of kind of variational flow matching approaches is that, you know, we can also parameterize this in terms of some form of posterior mean. And so previously what we saw is that, you know, we could define this velocity as some estimate of our mean endpoint minus where we are divided by the time left. You could do the same thing here, but now you have to somehow, right, introduce an extra index. So you have to say, kind of, given the interval st, I'm going to predict some form of mean endpoint. It's no longer as clear what the interpretation of that thing is. But if I now define the mean velocity by saying I'm going to take the difference between the endpoint and where I am right now, and I'm going to divide by the time left, then I once again have a velocity, and then I can multiply that by the time interval in order to get the displacement. So let's kind of do a plot again to kind of see if we can develop some intuition for kind of how that works. So if we want to kind of get this flow map, right? Like one way you could do this is you could just, you know, take this velocity and you could integrate a bunch of trajectories. And because this is a simple 2D problem, I can just do that. And so here what I've done is I've plotted a bunch of these trajectories. So, and what's kind of useful here, if you look at these flow lines, right, what you see is that everybody kind of converges towards the center, kind of at the start of the generation process. And then everybody diverges again later. And the reason for this is kind of what I told you about earlier, right? Like at the start, the posterior mean is just the mean of the data distribution, regardless of where you start. So like in the initial stages of generation, everybody is just going to move to the center of the data distribution. And that's why you get this kind of phase of convergence before you get kind of divergence again. And what that means is that these trajectories are curved, right? So I could pick one of these, right? Like they will have kind of some curvature that's very, very much kind of inherent to the way that we've defined this interpolation. Now, what would you do in variational flow matching, right? In variational flow matching, you're basically saying, move along this red line here, which is basically just a tangent of this golden curve at time 0. Now, suppose I pick a different point in time, right? Let's call that t. Like if I'm here along this trajectory, then I have a different tangent. So what's now the interpretation of this kind of mean endpoint? Well, basically, I need the point at time 1 on this axis such that if I move in the direction of that point, I will pass through the blue point here. That's the interpretation of the mean endpoint. So let me draw that. Yeah. So what you see is if I'm here and I know I need to get to here, then right, and I know I need to get to here. Then, you know, I could just pick the point here where if I interpolate between those points, I pass through this point, right? And so that's the, I guess, the geometric interpretation of this kind of mean endpoint. And now what you see is if you compare kind of, let's say, a two-step generation, well, if you use kind of the flow matching velocity, right, you're going to have a really big integration error. And so if you can somehow learn to approximate this flow map, you will stick kind of much closer to kind of the actual trajectory that you're supposed to have. That's the solution of your ODE. Okay, so how can you learn this flow map, right? Like, so I said earlier that this flow map is not a tractable quantity. And here I'd like to point to a paper by Nicholas Boffey, and I think he goes by Nick actually, Nick Boffey, and a bunch of co-authors, and they kind of write out kind of like a nice perspective on what kind of consistency conditions should you have for this kind of flow map if you've learned it. And one observation you can make is you can say, well, if this is the displacement over some interval, I can look at the limit of like an infinitely narrow interval. So then I get kind of like a point estimate. And so if I take the derivative of the displacement in the limit of an infinitely small interval, that by definition is the mean velocity kind of at the interval t to t, so like I guess like the kind of like infinitesimal interval. that should just be the velocity that you had in flow matching. So what's kind of nice is that this mean velocity in the flow map solution and the velocity in your flow matching, right, like they recover each other once you start considering an interval that is infinitesimally small. Now, what that also means is that you could now formulate conditions. And you can formulate these conditions by looking at the time derivative either at one end of the interval or at the other end of the interval. And so if you do kind of the far end of the interval, the end point, then you get this condition which people sometimes refer to, or which with Buffy and their co-authors refer to as the Lagrangian condition. So basically, if I have my flow map, I take the derivative with respect to the end point, then I should be able to take the instantaneous velocity at the end point, and those two things should be the same. Now, the other thing you can do is you can get an Eulerian condition, which is basically the equivalent of the Lagrangian condition, but now we're going to take the derivative with respect to the starting point, and then you need this kind of extra term in here in order to make things work out. So right now what we've written down are kind of mathematical conditions that kind of the true flow map would have to satisfy, right? And so what you can now ask yourself is, can I also kind of use this to define a loss? And so we'll do that in a second, but oh, yeah, sorry, there's one thing I forgot to mention. So like there's been a lot of work in this kind of general direction, and there's been 2 papers coming out in the last year that I think got kind of a fair amount of attention. There's this paper called kind of mean flows, which actually, when you kind of work it out, kind of implements this Eulerian condition. And then there was kind of a more recent paper, which got accepted in iClear on terminal velocity matching. So this is in the group of Kai-Ming He, and this is Jianmeng Song, who I think did his PhD with Stefano Armand back in the day. And so the terminal velocity matching implements the Lagrangian condition, and mean flows implements the Eulerian condition. And so what I really like about this paper by Buffy is that it kind of gives a unified perspective where you can just see that, you know, all of these are basically just different objectives for accomplishing the same thing. Okay, now in the context of our work on kind of variational flow matching, you can now also say, well, if I have categorical data, can I do a similar trick to what I did in variational flow matching, but for the flow map solution? And I alluded to this, right? Like I can represent this in terms of some form of mean endpoint. And so we have a paper under review now on something that we call categorical flow maps. And if you write everything out here, it's completely analogous to the normal flow map case. So you can write down this kind of consistency condition where now it's basically you see that this mean endpoint has to also be equal to the variational flow matching mean in the limit where S goes to T. And the Lagrangian condition, you can also write it out in terms of this mean. So this now leads us to kind of a way of doing the training. And so what you do when learning a flow map is, right, you begin by exploiting the fact that when S and T are equal, you have to recover the normal flow matching, and so then you can implement a normal flow matching loss, or in our case, a variational flow matching loss. And so that only kind of learns things for kind of cases where S is equal to T, but that gives you kind of like a baseline. And then given that learned baseline, you can now define a consistency loss. And so here's this kind of Lagrangian consistency loss. And what you get here is you get this time derivative. You get this term. We could call this, I guess, look ahead, right? So this is where you think you're going to end up at time 1 once you look ahead to where you're going to be at time t. And then this is the normal flow map. And so like the standard kind of Lagrangian consistency loss is kind of a squared loss. Floor also came up with, we call it an endpoint consistency loss. And this is something more analogous to just the self-supervised loss that you would have in variational flow matching. So it's a cross-entropy loss. And that works like this. You define a KL divergence. There's a slight kind of abusive notation here. And so what are you comparing, right? you're saying, okay, let's make a guess about where I'm going to be at time t. Then at time t, I'm going to evaluate this mean to get a guess of where I'm going to be at time 1. And I'm going to compare that to my guess of where I'm going to be at time 1, given where I was at time s. So basically, if I predict where I'm going to be at, if I kind of look at time t and predict where I'm going to end up in the data space, and I predict at time s where I'm going to end up in the data space, these two things should be consistent, and so the KL should be as small as possible. And then there's an extra term in here which basically says that, like, you know, the trajectory should be as smooth as possible. So this you could think of as a regularizer. And what Floor was able to show is that this loss is an upper bound on this loss. So that's this loss. And so what we do is we add both of these terms together in order to get that upper bound. Okay, so results here are remarkably good. So it's a little bit squiggly, I apologize for that. Like, here is our original cat flow work. And that required about 100 function evaluations during generation. And then if you look at kind of a benchmark like QM9, right, things you kind of measure are how many molecules are valid and how many are unique. Because if you have a very low uniqueness, it's easy to get high validity, so you want both to be high. Here at the bottom kind of are our flow map results. And so here we're using 1 or 2 function evaluations. Right? So this is just, I think cat flow you could also do it with 10, to be honest. But, like, you know, you're getting like at least a factor 5 to 10. And I guess relative to the reported results in the paper, you're getting a factor 50 to 100. And what you see here is, like, these numbers are not like, well, this is 99.8 and 99.9. And this is, let's see, with 2 steps, it's 97 and 96. But 97 and 96 is really not bad, especially for as little as 2 evaluations. And if you compare it to kind of the baselines that are kind of out there that do few step generation, it's a lot better than kind of the existing results. Now, the other thing that you can now do is you can integrate this into some form of test time inference procedure. This is actually my last slide, so I'll also stop here. Now, here what we did is we applied kind of sequential Monte Carlo. And it's a bit too much work to give a self-contained introduction to sequential Monte Carlo and how it's being used in this context. But at a high level, the idea is you use your approximate flow map to implement some form of guidance. That step is still approximate. So, like, you're not sampling from the true kind of guided distribution. So what you now do is, like your approximate guidance, you use this as a proposal and you compute kind of an importance weight to kind of correct for your discrepancy. And then once you have these importance weights, what you could do is you could take a little step, you can look at all the importance weights, and you can duplicate samples with probability proportional to these weights. That's how sequential Monte Carlo works. And so here you're investing kind of a larger amount of compute, but you can get good results. Here's kind of a little example from our work. So, you know, let's say that you're generating binary MNIST, and right now we only want to generate zeros. Then, you know, here's a comparison with kind of the kind of categorical flow map kind of look ahead compared to kind of some simpler baselines, for example, using variational flow matching to implement the look ahead. And again, you see that, you know, you get better FID scores and better average accuracy. So this is, I think, you know, for me, this is an example of where the puck is moving. I think if we're going to be solving kind of inference problems and design problems in kind of the physical sciences, I wouldn't be surprised if more and more we'll be using these kind of generative AI models and then building some test time inference on top of these generative AI models in order to get kind of good samples in a particular context. Okay, so I guess that brings me to the end of this talk/tutorial. So, you know, yeah, I guess the kind of theme of this workshop is AI across skills, and I guess that's a problem we think about a fair bit, right? Like, if you look at kind of the problems that, I don't know, or collaborators have, it could be anything from kind of molecular dynamics, where you need kind of upwards of 1,000 points. If you need to solve some form of problem in fluid mechanics, often you're upwards of kind of 10,000 points. And if you're doing kind of climate modeling, like, I don't know, if you need a whole Earth model of the ocean circulation, then you're talking about millions of points. And often you don't just need to run that thing once, right? Like I have a collaborator who does kind of these climate simulations in anger, right? And then one evaluation is like 3 months on a cluster or something like that. But the problem is that maybe then at the end you compare your model predictions to your actual kind of physical observations, and you realize, I don't know, something is not quite right. Like the salinity in the Indian Ocean is not what you observe in reality. So actually it turns out that you needed to run things with different initial conditions, or like a few kind of different constants that you're assuming in your model, right? So really what we would like to do are kind of calculations that are often very expensive. And we'd like to do them iteratively if we can, because we should really kind of solve for kind of the boundary conditions and or the unknown constants that give us best agreement with our observations. And I think in this setting, kind of these generative AI models can help us kind of converge in the right kind of part of the hypothesis space more easily. And I think really the ingredients here are going to be that, you know, we're going to implement some form of guidance, we're going to pre-train some model to generate kind of approximate solutions, and then we're going to define some sort of fitness criteria for kind of good solutions and bad solutions, and this can be a classifier, or more generally it can be some exponent of a reward. And where we'd like to get to is that we can now run some form of optimization or design kind of cycle. So like Bayesian optimization or Bayesian experimental design, where you either run a physical experiment or an expensive numerical kind of calculation to get data. Given kind of your results, you update your kind of model of your hypothesis space, and then you use some form of guided generative AI to evaluate what are the next points I should evaluate, what are the next simulations I should run, or what are the next experiments I should run. Now there's also kind of like a few more things about efficiency to say. So like today I haven't talked about work we do on architecture design. We have like kind of papers on kind of scalable attention in transformers. A nice paper is this work by Maxim Zhdanov on the architecture called Irving. And that can help, right? Like if you need to go to 1,000,000 points, one of the main problems in a transformer is that the quadratic self-attention for those 1,000,000 points becomes very expensive. I think we're getting better and better as a community of designing things that are closer to linear. And that at least makes these things kind of more into reach. I think for me, kind of when I talk to my kind of collaborators who are actually trying to do science, right? Like the big challenge is still how to do this on a budget. And like if your collaborator can do 100 experiments, then usually they have a pretty efficient kind of pipeline set up. And for an AI researcher, that's just a very small number of data points. And so I think we do still have to kind of bridge that gap. I think there's a lot of work on foundation models, and I think those foundation models can help. But I still see that there's just, like for most applications, like what you have as a foundation model is not close enough to what you need. And so you need something that's going to be just really data efficient as you're kind of running your experiments. And there's kind of one other question that I'd like to just throw out there. And like we're only working on this a little bit right now, but I think a question I have is, should our weights be encoding our data? Right now, all of these foundation models are really leveraging I guess, economies of scale, and I think these economies of scale have been quite miraculous. Like, we train on the entire internet, and then we know kind of a little bit about everything, but we're storing all of that knowledge in our weights. And somehow I feel it should be possible to kind of decouple a model that can reason about the structure of atoms or the structure of text from your knowledge of the world. And so I'm super interested in approaches that are efficient in the sense that they could use a much smaller set of parameters, possibly less training, but could then be kind of conditioned on large data sets at this time. All right, I'll stop there. Thank you all very much for being here and for your attention. So I've put kind of like all the papers that I've talked about today on this slide. If you're interested, I think you can find everything online. And it seems like we have a bit of time for questions, so thank you, and we'll be happy to take questions.
How much is the dependence on the noise distribution? Can you play around with it, like use non-Gaussian or like Gaussian with more variance, and will you then be able to generate like really crazy stuff, or is it like, as you said, it will always come to this kind of point where everything's like centered around that, and then from then on it spreads again?
Yeah, so I guess there were a bunch of questions in there, right? Like, and I think your questions were, does it matter what the distribution is that you start with, and have you experimented with that? So we have experimented with this a little bit, and my sense is that it doesn't matter so much. But, right, like, I think, right, what people do a lot is this kind of mini batch optimal transport stuff, where if you'd, right, where you'd somehow like to do the interpolation in a way that's not independent. So like the way I've described it today in the tutorial is you pick from a Gaussian, you pick from the data, and you draw a line between the two, right? You could also say, I pick from the data, and then conditioned on the data, I pick my noise. And then you're able to kind of define criteria. For example, you could define some form of optimal transport style objective where you say, I want each of my noise points to be as close as possible to my original data points. And it does seem like those kind of things can help in certain contexts, so it's certainly not useless. I think for me, the lesson from kind of the flow matching literature is that, you know, we spent a lot of time thinking about kind of noise schedules and all these kind of things, and actually a really simple linear interpolation between data and Gaussian noise works quite well in quite a lot of cases. So, right, it's probably where you should start, and you can get some gains by doing something a bit different, but it does seem a little bit diminishing returns in my experience.
Yeah, given the tutorial aspect, I would like to ask you, stochastic interpolants, is it just the same thing as as flow matching, or would you say that there's some differences?
I think stochastic interpolance is a slightly generalized formulation of the interpolation you also have in flow matching, right? And it actually kind of like, it goes to the previous question. So the stochastic interpolant setup says you have an arbitrary distribution at time 0 and an arbitrary distribution at time 1, and you have a schedule, and you can also introduce some Gaussian noise along the way. And so if you write out what you need to approximate in the general stochastic interpolant setting is, given your noisy data point, you need the mean of your data points at time 0, and you need the mean of the data points at time 1. So if you, right, like if at time 0 your noise is Gaussian, the mean is always 0, so then you can just get rid of that one and it simplifies. In the general setup, you need to do a little bit more work. What I'm personally not aware of is kind of cases in which that added generality kind of translates to kind of big performance differences, which doesn't mean that they don't exist, right? Like I don't know every paper. Yeah.
Is there a relationship between flow maps and rectify flows?
I'm sure, but I wouldn't be able to tell you right now what that relationship is.
Okay, thank you very much for the great talk.
Sure.
So I would like to ask you to come back to the question of efficiency and cost of, cost of all these models. So I am always surprised that we don't look at divide and conquer approach. So I mean, the idea of building a big, generative model and then condition it, or that's okay. But don't you think that you could imagine that could be interesting in some cases to have several smaller models dedicated maybe to the partition of the some areas of the support of the distribution you want to model.
I see. So your question is, could you do this using specialized models for different subsets of your data distribution?
Yeah, mixture of experts,
Sure.
renewed a little bit the LLM by somehow reducing the cost of computation. And do you think they are useful?
Yeah, so at least at an intuitive level, this makes sense to me, right? And it makes sense if you think about the properties of the interpolation. So, right, like in this interpolation, everything is easy at the start and everything is easy at the end, right? Because at the end, you're just looking up kind of the nearest neighbors in the training data and moving towards those nearest neighbors. Now, of course, that doesn't mean that your model is doing that, right? Like your model doesn't necessarily memorize all your training data, and there's some suggestion that actually the generalization emerges from the fact that we can't memorize our training data, right? But conceptually, like it feels like the computational problem that you're approximating is easy when you're close to the data. The computational problem that you're approximating is also easy when you're close to the noise, because there it doesn't matter where you are, you should always just move to the center of mass of the data. And that does kind of suggest that maybe the type of model you need close to the noise and the type of model that you need close to the data is a bit different, and maybe you could have some form of product of experts thing that switches between those two during integration, right? Like it's not implausible. Yeah.
There's another one.
Sure.
I read the 2025 paper with about guidance. And you mentioned there, and I didn't really exactly, and I didn't really understand the reason. You say that the guidance or the addition of the likelihood term with your proposition, it works well when somehow when this data that you use for guidance is not so informative, such that your posterior is sort of similar to your prior. Is that related to the statements you were making later, where you basically were saying that the mapping would be approximate, or is it something fundamental? I didn't get it.
Yeah, I have to remember exactly what, was that in context of the Laplace approximation or in context of just generally as a statement? I mean, obviously the guidance problem is easier if your data is non-informative, because then like your posterior would be like your prior.
Get it. I mean, you I guess maybe there was the Laplace and the equations that you then used for the combinations, and I just didn't appreciate what was the...
I think the main thing I would say is like, when we tried this Laplace approximation in that paper, I don't think that's what I would do today. Because like, think about kind of the setting where you have a classifier, then doing a Laplace approximation to a classifier may not work well, right? Because a classifier says, like usually it's kind of like a step function, right? Like if I'm in the right region of sample space, then the classifier will be 1. If I'm in the wrong region of sample space, it'll be 0, and there's some decision boundary where it crosses over. And so if that's the function you're Laplace approximating, right, like that's not always the best.
It's not related to the approximation, because you define the likelihood on the endpoint, and if you do guidance, I guess, with diffusion models, you need to estimate this likelihood score during for sort of an XT.
Yeah, so that's a trade-off, right?
Yeah.
Like, so that's exactly right. What you're kind of, right, you need to estimate, right, this thing, and this thing is an expected value, right? Like, suppose that you define this not in terms of your noisy z, but in terms of your x, then you need to take an expectation with respect to all x's that you could get from your z in order to compute the probability of a label given z, right? And so I think jury is still a bit out on what the best ways to do this are, right? I alluded to that kind of SMC is becoming more and more popular. I think that kind of the interaction with these flow map methods is useful because like those flow map methods give you kind of a better guess of where you're going to be at time one. And when you have a better guess, then the amount of inference you have to do on top of that becomes kind of less. Yeah.
Thank you.
All right, everyone. Thank you very much.